Hello everyone. Let's see how we can solve the jump game problem. So we are given an array of integers and at each position we have the number of jumps that we can jump forward from this position. So for example, at this initial position, we can jump 2 positions maximum. We can jump to this position or this position. If we are standing here, we can jump 3 positions maximum. We can jump to this one or this one or this one. Initially, we will be standing at the initial position right here, and we should check if we can reach the last index right here. If we can reach it, we should return true, else we should return false. So let's go to the canvas and discuss. So let's take the first example. We are initially standing at this index. Our options are either to jump here or either to jump here. So if we are standing at this index, number 2, and index is 0, we can either jump to number 3, which is at index 1, or we can jump to number 1, which is at index 2. If we choose to jump to number 3, which is at index 1, so we have either the option to jump here, or here, or here, because the number 3 means we can jump maximum 3 positions ahead. So here we can have 3 options, which are either to jump to this position, which is 1 at index 2, or this position, which is 1 at index 3, or this position, which is 4 at index 4. As you can see, this brute force approach makes our cases grow exponentially, which is very, very inefficient. So we must find another way to solve the problem. If we are standing here at the initial position, what is the maximum reachable index that we can see from this position? So if we are starting at the initial position, what is the maximum index that from this position we can reach? It is the index of this position, which is 0, plus the maximum number of jumps, which is 2. So the max number of jumps plus the index gives us the number 2, which is the maximum index that we can reach, which is here at this position. Is this the last position? No. Okay, let's try another point. So at this position right here, the maximum reachable index from this position, remember that 2 is the current maximum reachable position that we have seen so far. At this I, when I is equal to 1, so we are standing at this index, we have number 3. This means that we can go from position index 1 and go 3 jumps ahead until we reach the index number 4. This is a new maximum reachable index that we have seen right now, and it is larger than the 2 that we have before. So we update this to make it equal to 4. And if you notice that this 4 right here, so this is the maximum reachable index that we have seen so far. This means that for this I and for all the numbers that we have checked before it, so for all these numbers, this 4 is the maximum index that we can reach if we take any of these numbers. Okay, and if you notice also, this 4 is equal to n minus 1, where n is the size of the array. As you can see, the last index is 4. So if we stand at this position, we can reach the last position. So the answer in this case will be true. And we do not need even to check these numbers. Let's check if our algorithm also applies for the second example. So on the second example, we start right here at index 0. So the maximum reachable index, before we start iterating over the array, the maximum reachable index is equal to 0. Because before iterating on the array, we have not seen any of the numbers of the array. So the only thing that we are sure about is that we can reach the first index, which is at I equal to 0. So this will be our initial maximum reachable index. So when I equal to 0, standing at this position tells us that the current maximum reachable position, let's call it Ri, reachable index, current reachable index. It's equal to 0 plus 3. So 0 plus the number of jumps that we can jump from position 0, it's equal to 3. So from position 0 right here, the maximum position we can reach is 1, 2, 3. 3 jumps right here. Okay. So the reachable index is larger than the current maximum reachable index. So we update the current maximum reachable index and set it to 3. And we move I forward. So now I is equal to 1. And the nums of I is equal to 2. So reachable index right now will be the index 1 plus max jumps. It will be equal to 3. So the reachable index that we have seen in this iteration is equal to the maximum reachable index that we have seen for all the numbers before this iteration. So we don't do anything. We just advance I, hoping that we can get a better maximum reachable index. So if I is equal to 2, this means that we are at index 2 right here. The maximum reachable index, the reachable index right now, it will be I, which is 2, plus nums of I is equal to 1. So this is equal to 3. So we still have not found a better maximum reachable index. So we advance I. So I now is here at index 3. So I is equal to 3. So now the reachable index, when we are standing at this position, it will be equal to the index, which is 3, plus the maximum jumps we can jump from here, which is 0. This is interesting. So the reachable index is 3, and I is also equal to 3. So these two pieces of information tell us that if we are standing at this position I equal to 3, then the maximum position that we can reach is 3, which is the same index we are standing at. So we are stuck at this index. And this piece of information now tells us that for all the numbers before I equal 3, so for all these numbers, the maximum position that we can reach, if we started from any one of these numbers, it will be also 3. So this means that for sure, for this array, when we reach the index I equal to 3, we are stuck and we cannot move further. So the answer would be false. So let's code the solution. Let's write the pseudocode first, and then we can write the code in the website. So we will need, of course, I, which is the iterator. So let's say for every I, while I is less than n minus 1. Why I am saying that I should be less than n minus 1? Because if I reaches n minus 1, we should return true. We should not try anything further because we already have reached the condition that makes us return true. So while I is less than n minus 1 and initially I is equal to 0 and our maximum reachable index is also equal to 0 initially. So while I is less than n minus 1, every time what should we do? We should calculate the current reachable index, so it will be equal to I plus nums of I. And we need to check if the reachable index that we have seen standing at the current position is larger than or equal n minus 1. So we already have seen that we are standing at a position, and from this position we can reach the last index. So in this case, we immediately return true. We don't need to try the other numbers. And we should put our stop condition, which is if the reachable index at the current place we are standing at, if it's equal to the current place, and if the maximum reachable index is less than or equal the current place. So if we are standing at an index, for example, this index right here, if we are standing at this index, then Ri, which is the reachable index from this index, it will be equal to I. And we also will have maximum reachable index. So for all these numbers that we have tried before, the maximum index that we can reach is already this I or less than this I. So in this case, we don't need to try any other numbers. We are already stuck. So we just return false because we cannot get past this index. And we should also check if for this position we are starting at, we are standing at. So if this is not true and this is not true, so if these two ifs do not return, then this current index might have a jump that makes the Ri larger than the MRI. So if the reachable index from this position is larger than MRI, which is the reachable index that we have seen so far, the maximum reachable index that we have seen so far, so we just update the MRI. So MRI it's equal to Ri. And finally, we advance I by one position. And if we get out of the loop, this means that the condition has been false, which is I is less than n minus 1. So at this point right here, we can know that I is equal to n minus 1, so we just return true. Because I equal n minus 1 means that we have already reached the last index. Let's code the solution. So as we said, I is equal to 0 and MRI starts at 0. And while I is less than the last index, which is num size minus 1, we are going to say if we're going first to define the reachable index from this position. So this will be the max reachable index that we have seen so far, and Ri will be equal to I plus nums of I, and this will be the max reachable index from position I, means from index I. So if Ri is larger than or equal num size minus 1, so this means that the current position we are standing at, this position can lead us to directly jump to the last index, so we should return true because we found a solution. And if the current reachable index, so if we are standing at a position I and the maximum index that we can reach from this position I is I itself, so we cannot go further. And if the maximum reachable index, so if none of the other numbers that we have seen before can let us also pass through I, so if MRI is also equal to I, then we should return false because we are stuck at this position. We cannot try the next numbers because of, for example, right here, if we are at this number, so Ri, it will be equal to I. So from this number, we can jump 0 jumps. So Ri is equal to I. We cannot go further. And MRI, for all these numbers, the maximum reachable index we can reach is this index, is this position. So we are stuck here. We cannot even try these numbers to the right because we cannot reach them. And if none of these conditions is true, so we are standing at a number that might hold a solution later. So what we should do is just check if the reachable index from the current position, if it's larger than the maximum reachable index that we have seen so far, then we just update the maximum reachable index, so it's equal to Ri, and we just advance I by 1. And finally, we can return true. So let's submit it and hope it works from the first time. And thankfully it works. The time complexity of this solution is O of n, because as you can see, we are only looping through the array once. We have no nested loops or anything else. And even we are optimizing it more because we are exiting earlier. And also, The space complexity is also O1 because we only are defining some few variables and not arrays that depend on the size of the input. So this solution is both optimal in terms of time complexity and space complexity. Thank you very much. In the next video, we're going to solve the jump game too, so stay tuned. Bye bye.